Hey everybody, and welcome to this video on using the point-slope form of a linear equation. So let's get to it. Alright, in this video, we're going to learn how to use the point-slope form of a linear equation to model some real-world situations. So suppose that you're the superintendent for your town. You know that the larger your town gets, the more money you will receive from both the state and federal government to fund schools, police, libraries, roads, transportation, and any other public works. So it's important for you to keep track of how many people are in your town. In 1990, there were 240,000 people in the town. However, the population of the town had been and continued to grow at a constant rate of 20,000 people every year. So how can we model this situation? First things first, let's define some variables. Let's let the dependent variable be the population in thousands, and we'll give that the variable n. And let's let the independent variable be the year, and we'll give that the variable k. Okay, so my claim is we have one piece of data about in what year what the population of the town was. In 1990, there were 240,000 people in the town. And my claim is we can make an ordered pair out of that piece of data. And note, all of our ordered pairs are going to be of the form k, comma, n, right? Year, comma, population in thousands. So my claim is we can take this piece of data and write it as an ordered pair, 1990, comma, 240. Now note that we also have a rate of change for this population, that every single year that goes by, the population grows by 20,000 people. And note that the population of this town is growing at a constant rate. The rate of change never ever changes. So if you were to graph this population, it would actually be a line. That's why we're going to model it using a linear equation. So my claim is that 20,000 people every year represents the change in our population over the change in years. That's our slope. In this case, we would say our slope is 20, because of course we're working in thousands. So now we have an ordered pair from our situation, and we have a slope. And my claim is, using these two pieces of information, we can easily create an equation to model this situation using the point-slope form of a linear equation. And so the equation would be n minus 240 equals 20 times k minus 1990. And remember before how we talked about there are multiple ways of writing this exact same equation. And in this case, my favorite way to write it is as n equals 240 plus 20 times the quantity k minus 1990. Here it's clear that in the year 1990, there were exactly 240,000 people in the town. 240,000 people is kind of like the starting value of our population in the year 1990. And that, of course, this number grew by 20 every year. Of course, that 20 represents 20,000. Now note, we could put this equation in a slope-intercept form if we'd like, but it looks a little weird. We got a very weird looking n-intercept. And why might that be the case? Well, remember that the n-intercept happens when k is 0. That is, the n-intercept represents the population of the town in the year 0. Remember, we're assuming that the town had been growing at that constant rate of 20,000 pretty much forever. And if that were the case, the population of the town would be negative in the year 0. Of course, this doesn't make sense, which speaks to the shortcoming of using a linear model, but it also goes to show how it may be best to leave our equation in point-slope form. Now that we have our equation, it's easy to do some modeling problems, right? You tell us the year, we'll find the population. Or someone tells us the population, we can figure out the year in which that population will happen. So for example, if we want to determine when the population will reach 800,000, all we need to do is substitute 800,000 in for our population variable. Of course, we're going to have to substitute in 800 because our variable is in thousands. Of course, we could just as easily use this equation to determine what the population would be in the year 2020. We just substitute 2020 in for our year variable. Now, there is a different way that we could have defined our variables, which may have made our lives a little easier. If we define our variables to be the number of years since 1990, then instead of having the ordered pair 1990, 240, we'd have the ordered pair 0, 240, which is our n-intercept, which will be a lot easier to work with. In this case, we're now looking for the equation of a line still with the same slope of 20, but with an intercept of 240. And that one's obvious. That'll just be n equals 240 plus 20k. This is just like one of the equations we made back in the day. And now we can use this new equation to answer the exact same questions as before. Note that in this case, when we substitute 800 in for the population, we do not get the same answer we did before. However, note that this new number represents the years since 1990. So when we calculate what year that means, we end up with the exact same result as we did before. Now, in order to find the population in the year 2020, we need to substitute a different number in for the variable. Note that here, we would just substitute 30, as 2020 is 30 years after 1990. Of course, we're going to end up with the exact same result as we did before, again. Alright, let's try another. When you buy a house in the year 2012, you need to take out a $180,000 loan to do so. The agreement you have with the bank is that you will pay back the loan at a rate of $7,500 a year until it is completely paid off and you owe no more money. Okay, first things first, let's define some variables. Let's let the dependent variable be the amount that you owe in thousands, and we'll give that the variable D. And let's let the independent variable be the year, which we will call N. Alright, so how are we going to model this situation? Well, I claim that we have one piece of data about a year and how much money you owe in that year. My claim is that in 2012, you owe $180,000. So my claim is that we have one ordered pair of information, namely 2012, 180. Note that we also have a rate of change, or slope, for how much you owe. Remember, we pay back the loan at a rate of $7,500 a year. That rate is exactly the same all the time. So if you were to graph this situation, it would be a line, and that's why it's okay to model it with a linear equation. And my claim is that the slope in this case is negative 7.5. 7.5 represents $7,500, and that's how much less you owe every 1 year. So now that we have a rate of change, or a slope, and an ordered pair, we're ready to use these two pieces of information to create an equation to model this relationship using the point-slope form of a linear equation. Alright, in this case, our equation would be D minus 180 equals negative 7.5 times the quantity N minus 2012. Again, I don't prefer the point-slope form of the equation as much as I prefer this one. D equals 180 minus 7.5 times the quantity N minus 2012. Here it's clear that you start by owing $180,000 in the year 2012, and that amount decreases by $7,500 every year. One more note, if we went ahead and put this equation in a slope-intercept form, we would get a crazy intercept. Remember that the D-intercept here represents how much you would owe the bank when N equals 0. That is, in the year 0. It's as if you've been paying the bank back $7,500 a year since the birth of Christ. And now it's just $180,000. So back then it would have been absolutely huge how much you owe them. So in this case, let's just go ahead and use this form of the equation. I think it's going to be much more relevant and informative. Alright, now we've got this equation. If we were to be given a year, we could tell exactly how much we owe. If we're given an amount that we owe, we could find out exactly in what year we owe that amount. So let's go ahead and do some practice. So let's use this equation to determine how much we'd owe the bank in the year 2027. No problem. All we need to do is substitute 2027 into our variable representing the year and then solve for how much we owe. Alright, now let's use the equation to determine when we're going to pay off the entire loan and owe no more money. Well, of course, if we owe no more money, that means that the value of D is 0. So all we need to do is substitute 0 in for D and solve for N to find out in what year that will be. Of course, we could have been a little bit tricky, and if we had defined n to be the number of years since 2012, then we'd have a much simpler equation. We just said d equals 180 minus 7.5n. It's the exact same relationship that we're capturing, just with slightly differently defined variables, which made for a much simpler equation. Alright, let's do another example. And now I hope you're starting to get the hang of this and might be able to start anticipating and doing some of these on your own. Alright, in 1963, the median family income in the United States was $40,000. Since then, it has grown an average rate of $120 every year. Now, first things first, let's define our variables. Let's let our dependent variable be the median family income, just in dollars, and we're going to call that P. And let's let our independent variable be the year, which we'll call H. Now, why don't you try pausing the video, finding an ordered pair, finding a slope, and create an equation in point-slope form, and when you're done, we'll play the video and reconvene. Alright, in this case, we're looking for an ordered pair H, P, the year and what the median family income was in that year. And we definitely have that information. In 1963, the median family income was $40,000. So we can create the ordered pair 1963, 40,000. Note that since that median family income has grown at the same average rate every year, that means if we were to graph it, it would be a line, so we can use a linear equation to model it. In this case, the slope, or the rate of change, is 120, because every year that goes by, the median family income goes up by the same $120. Now that we've got an ordered pair and a slope, we're ready to model this situation using the point-slope form of a linear equation. In this case, our equation would be P minus 40,000 equals 120 times the quantity H minus 1963. Or of course, the way I prefer, P equals 40,000 plus 120 times the quantity H minus 1963. The starting value for a median family income was $40,000. This happened in 1963, and it grew at a rate of 120 every year. Now that we've got this equation, we can go ahead, and if we are told any year, we can substitute it in for our year variable and find the median family income. Of course, if we're told the median family income, we could substitute it in for this variable, and we can solve for the year to figure out in what year that was the median family income. Of course, if we had defined a new variable, m, to be the number of years since 1963, the equation would have been a lot simpler. It would have just been P equals 40,000 plus 120m. Very similar to the simpler types of equations we came up with earlier. Alright guys, that's it for this video. I hope you found it helpful, and I hope you enjoyed.